Hello everyone, this is Professor DePaulo welcoming you back to Psych 220, Behavioral Statistics fully online, and we're going to be talking about in this lecture Chapter 5, which is on z-scores and standardized distributions. So the learning objectives for Chapter 5 is to understand what the z-score is, to figure out the formula of the z-score, to transform x values into the z-scores, to transform z-scores back into x values, to describe the effect of standardizing a distribution, and to transform scores to a standardized distribution. So basically all of this involves very, very basic algebra. Nothing complicated, just solving for a variable, isolating a variable, solving proportions. It's not difficult at all. This is very basic algebra that you should all be familiar with and able to do for this chapter. So the purpose of z-scores is to basically be able to put all the scores on an even playing field. And what I mean by that is to be able to compare across different scores that may have been measured in a different manner. For example, taking one particular class at one university versus a different class at another university. Let's say your friend is taking organic chemistry at Columbia. It's a great class, by the way. One of my favorite classes of all time, organic chemistry. Some of you may have taken it already. Some of you may be willing to take it, but it's just a wonderful class. It's like mathematics with molecules. So your friend took organic chemistry at Columbia, and you took organic chemistry at BMCC. And you scored a B in your BMCC class, and your friend scored a C at Columbia. You want to know who did better in the organic chemistry class. That's the question you're asking. Well, you can't compare because technically you got a B and your friend got a C, and so you did better, right? But then you took it at BMCC and they took it at Columbia. I'm not saying there's a difference there because some courses at BMCC can be as challenging as courses at Columbia, but the difference in instructors may have influenced the scores. So therefore, we need to look at how well did you do in your class compared to everybody else that took the same class. Because now the playing field is even. Everybody took the same class with the same professor, and they got a grade. And now you want to compare your score to them. And then how did your friend do at Columbia in their class with, compared to other students in that class with the same professor? And then if they did better relative to their class compared to what you did relative to your class at BMCC, then they did better. And vice versa, right? If you did better at BMCC compared to everybody else at BMCC, when compared to your friend at Columbia compared to the other students at Columbia. What we're doing is we're creating a z-score, and a z-score is basically your position in a distribution relative to everybody else. So technically, the z-score tells us how many standard deviations above or below the mean is your score located, right? And therefore, I know like how you perform relative to everybody else. So if you scored 2 standard deviations above the mean, which means you had a z-score of +2, that's pretty good. That means you scored better than almost everybody in the class, right? Because you had people that scored closer to the mean. You had people that scored much less than the mean. So if you scored 2 standard deviations above the mean, which is equivalent to a z-score of +2, you were one of the top people in the class. If you scored a z-score of -2, unfortunately, you're one of the bottom people in the class. And if you scored a z-score of 0, that means you're exactly average. You scored the average. And so z-scores tell us where you're located relative to everybody else in terms of standard deviation units. You have both positive z-scores and negative z-scores. And they allow us to compare different metrics. So I can compare your z-score compared to your friend's z-score at Columbia in the same class with different teachers. and see who did better relative to the other students in those classes. And that's a good measure of who did better comparing the two of you. These are very dissimilar metrics because it's not standardized, right? You had different professors at different universities. So that's the importance of z-scores. And they help us calculate things like correlation, coefficients, which we're going to be doing later in the course. They're just useful. They also help us detect outliers. So if someone scores very high in terms of the z-score or very low in terms of the z-score, then they are dissimilar to everybody else, and they're termed an outlier. And identifying outliers is important because they can really screw up our data sets and our data analysis. So it's useful to use z-scores to identify outliers. And you're going to be doing this in the lab 1, right? So, and there's another discussion for that. Here's an example of a particular score that has 2 different z-scores relative to the distribution that it's in. So if you look at figure A, the mean is 70, the standard deviation is 3, and the person scored 76. So if we just look at the z-score, they scored 2 standard deviations above the mean, they would have a z-score of 2, positive 2, in picture A on the left. If you look at picture B on the right, the person scored 76 again, but here the standard deviation is much larger, it's 12. So if I were to calculate the z-score here, it would be 76 minus 70 over 12, which would give me 6 over 12, which would give me 1/2, positive 0.5. So you have the same raw score of 76, but in figure A, it corresponds to a z-score of positive 2. In figure B, it corresponds to a z-score of positive 0.5. So if we're looking at exams, or exam score, if your exam score was 76 and you were on the left here in figure A, you feel pretty good because you scored almost the top score in the class. In figure B on the right, though, if your exam score was 76, you should feel okay, but you don't feel super excited because your z-score is only 0.5, positive 0.5, which means you scored above the mean, which is sometimes good, right? However, you didn't score as well as some of the other students in the class. So if you're a student in class A, you're happy. If you're a student in class B, you're kind of like, yeah, I did okay, but I wish I would have done better. Obviously, it's better than scoring on the left, but you know, you're doing better in class A here. So the sign of your z-score tells you whether the score is located above or below the mean, and the number tells us the number of standard deviation units above or below the mean. It's as simple as that. And there's a z-score for population, and there's a z-score for sample, but it basically boils down to the raw score, which is your x, minus the mean, whether it's a population mean or a sample mean, doesn't matter, divided by the standard deviation. Could be of the population, it could be of the sample, depending on what you have access to, right? So it's always raw score minus the mean divided by the standard deviation. And that gives you the z-score, and that tells you is that raw score above or below the mean, and how many standard deviation units above or below the mean is that raw score. And this is kind of what a normal distribution would look like in terms of z-scores. Most of the people, if you have a normal distribution, most of the people are scoring in the middle of the curve. So the majority are scoring between 1 standard deviation below the mean, which here is -1, and 1 standard deviation above the mean, which here is +1. So you have a majority of cases between -1 and +1 here in the normal distribution. As you get further away, you get to +2 and -2, you have almost all the cases that fall between -2 z-score and +2 z-score. That contains almost every case. You have very few cases that go beyond both +2 and -2. Most of the cases fall around the mean. You see, the mean is always 0, The mean of the z-scores is always 0, and you see that the vast majority of cases are falling very close to the mean in a normal distribution. The standard deviation of the z-score distribution is always 1. Here's the formula that I discussed for the population. Z is x minus mu. Mu is the population mean, divided by sigma, which is the population standard deviation. So it's raw score minus population mean divided by population standard deviation. And that gives you z-score. The z-score is always expressed in standard deviation units, either above the mean, which is positive, or below the mean, which is negative. If I do a little algebra here, and I rearrange this, if I solve this proportion, and I'm solving for x, I get z times sigma equals x minus mu. If I add mu to both sides, I get z sigma plus mu equals x. And that's what you have on the right of this equation. So all I did was I solved the proportion and solved for x. So x, the raw score, is equal to the mean plus the z-score times the standard deviation. That's all it is. So just manipulating this slightly algebraically gives you the formula for the raw score. We use populations most of the time for computing z-scores if we're comparing the individual to the population at large, and we want to see is this particular individual an outlier in this population, or where do they fall with regards to the population? We're computing z-scores. So z-scores are very frequently used when we're comparing to populations, but we can also use z-scores for samples. And we can use the z-scores of a sample to then calculate what's called the normal variant z-test. So we can actually compare a sample mean to a population mean and compute z-scores that way. And we won't be doing that until a little bit later on. But you can calculate z-scores individually, but you can also calculate z-scores with samples as well. It works the same way though. The z-score tells us the relative position of each individual score to the mean in terms of standard deviation units. The distribution of z-scores maintains the same shape as the original distribution. So if the original distribution is skewed and we convert those raw scores into z-scores, the distribution of z-scores will be skewed. So it's not like some magical formula that takes a skewed distribution and makes it normal. It doesn't. The shape of the original distribution will be the same shape as the resulting z-score distribution. All you're doing is a linear transformation. So let's look at a couple of brief problems. Here we have a z-score of 1. What does that mean? Does that mean that the score is above the mean by 1 point? Does that mean that the score is above the mean by 1 standard deviation? Does it mean the score is below the mean by 1 point? Or does it mean the score is below the mean by 1 standard deviation? Well, it's positive, so it's certainly not below the mean. So C and D are ruled out. And what does a z-score of 1 mean? That means it's 1 standard deviation above the mean, so it's obviously B. A z-score of 1 corresponds to exactly 1 standard deviation above the mean. Let's look at another basic problem here about z-scores. True or false? A negative z-score always indicates a location below the mean. Well, that's true because a negative z-score means that the score falls below the mean. Because if it scored above the mean, it would be positive. And if the score was exactly equal to the mean, the z-score would be 0. So therefore, a negative z-score must fall below the mean. True. A score close to the mean has a z-score close to 1. Well, no. Because the mean, the z-score, the mean in terms of z-score is 0. So a z-score of 0 is the mean. So any score that's close to the mean has to be close to 0, not 1. So that is obviously false. We want the z-scores close to 0 if they're close to the mean. So the mean of the z distribution is always 0. The standard deviation is always 1. A z-score establishes the relationship between the raw score, the mean, and the standard deviation. So if you're given a mean, a raw score, and a z-score, you can simply solve for the standard deviation. So it's that same formula. Z equals x minus the mean divided by the standard deviation. And if you have 3 of those 4 items, you can solve for the one unknown algebraically. So in this case, it would be z times sigma is x minus mu. So it would be x minus mu divided by z would give you the value of sigma. So I just rearranged the formula. So you should be able to algebraically manipulate these very basic equations. These are not complicated. You're only solving for one unknown. If you could solve a proportion, and you know how to add and subtract, multiply and divide from each side of the equation, this should not be difficult. This is remedial algebra. Let's look at another couple of problems here. For a population with a mean of 50 and a standard deviation of 10, what is the x value corresponding to a z of 0.4? Well, a z of 0.4 is 0.4 standard deviations above the mean. Sigma here is 10. So 0.4 of 10 is going to give me 4. So this x value that corresponds to a z of positive 0.4 is going to be 50 plus 4 units above the mean. So if I add 50 to 4, I get 54. So this is once again solving for the equation, right? So x equals z times sigma plus mu. Z times sigma is 10 times 0.4 is 4. Added to mu, which is 50. 50 plus 4 is 54. So the answer has to be C, 54. And that is the answer. So all you're doing is plug into this basic equation and solve it for the unknown. Let's look at the next 2 questions here, true or false. If mu is 40, so the mean of the population is 40, and 50 corresponds to a z of 2, then sigma is 10 points. So if the z-score is positive 2, that means it's 2 standard deviations above the mean. If the mean is 40, and it's 2 standard deviations above the mean, and the standard deviation is 10, so something with a z-score of 2 would have to be 2 times 10, which is 20. Points above 40 would be 60. So 50 does not correspond to a z-score of 2. 50 would correspond to a z-score of positive 1. So that first statement is false. If I wanted a value to correspond to a z-score of 2 here, if I wanted 50 to correspond to a z-score of 2, then sigma would have to be 5 points. The standard deviation would have to be 5 instead of 10. The second statement, if sigma is 20, a score above the mean by 10 points will have a z equal to 1. Well, in this situation, if sigma is 20, a score above the mean by 10 points would have a z equal to 1. Well, if sigma is 20, then something that's 10 points above the mean would have a z-score of half of 0.5, because 10 points is half of 20, and 20 is the standard deviation. So that statement can't be correct, because if they're only 10 points above the mean, they should only have a z-score of 0.5 instead of 1. If there were 20 points above the mean, then they would have a z-score of 1, given that sigma, the standard deviation, is 20. So that statement is obviously false as well. Both statements are false. In the first statement, sigma would have to be 0.5. Sigma would have to be 5. In the second problem, z would have to be 0.5 if they were 10 points above the mean. So this is once again plug into the equation. You could do this in your head because the numbers are rather simple here. You can do it in your head, but if you need to do it on paper, do it on paper. If you need a calculator, use a calculator. I try to like not over rely on a calculator because you know you become like kind of crippled by the calculator, and a lot of students just can't do anything without a calculator. But if you need the calculator to double check your answer, then by all means use it. If you need a piece of paper, use it. Scrap paper, use it. There's nothing wrong with that. If you can do it in your head, fine, then do it in your head. Whatever works for you works for me. So as I was mentioning, you could transform every x value into a z-score. And we know that the z-score distribution has the same shape as the original distribution. The mean is always 0 of a z-score distribution, and the standard deviation is always 1. The z-score distribution is also called the standardized distribution. And if it's normally distributed, it would be called the standard normal distribution. And that's a very special distribution that we're going to be examining in more depth later on, the standard normal distribution. So if I'm transferring my x to z here, and this would be the case, is if I'm transferring the 100 and the mean is 100, then I know that a score of 1, standard deviation is 10. The score of 110 is 1 standard deviation above the mean. The score of 120 is 2 standard deviations above the mean, etc. So it's a very easy transfer from, all I do is subtract the mean and divide by sigma, and that gives me the corresponding z-score. And it's just a linear transformation. You're not changing the shape of anything. All you're doing is changing the mean to 0 and the standard deviation to 1. The scores relative to each other will always stay the same. So for instance, if I'm transferring a score of 100 into a z-score, if I subtract 100 and divide by 10, I get a z-score of 0, the mean. If I'm trying to transfer 110 into a z-score, I subtract 100 and I divide by 10, I'm getting a z-score of positive 1. So sigma is always 1 here, and the mean is always 0. So nothing mind-shattering here. The key bonus point of the z-scores that I had mentioned previously is that you can compare them across different types of distributions because they've been converted to the same scale. So you can compare IQ across a wide variety of IQ tests because IQ has been standardized to have a mean of 100 and a standard deviation of 15. So no matter what type of IQ test you take, the mean is going to be 100 and the standard deviation is going to be 15, and therefore we can compare IQs of people across different IQ tests. Now, we assume that these tests all measure intelligence in the same manner, right? But there's a wide variety of IQ tests. You know, you originally had the Stanford-Binet, then you had you have the Wechsler intelligence scales. Now you have the Wechsler intelligence scale for children. You have the Wechsler adult intelligence scale, the WAIS. So there's a wide variety of different measures of intelligence, but they all are standardized. They're all converted to the same metric. So the first thing that happens is you convert the scores to z-scores, and then you convert them to a mean of 100 and a standard deviation of 15, and that gives you your IQ. Because it's just easier talking about IQ of 100, which is average, rather than saying your IQ is 0, because the z-score would be 0. So you don't want to say your IQ is 0 or your IQ is 1. That doesn't sound that great. So they'd rather, instead of using z-scores to measure IQ, they'd rather convert it to a scale with 100 being the mean and 15 being a standard deviation. It just sounds better and it's easier for people to follow. Same thing happens with SAT scores. So mean of SAT is 500, standard deviation is 100. And that's for all the sections, right? That's the math section, the verbal section, and there's, I don't know if they had a writing section, but it was scored differently. I don't know what they're doing. They keep changing it. They used to just have math and verbal for SAT, and it was up to 1,600, but now it's exploded. It's what, 2,400? I don't even know what they keep changing it. For those that have actually taken the test, now we can argue whether or not, just because we know how to measure it and we know the mean of the standard deviation doesn't mean that it's a good measure. That's a completely different story. We can disagree about IQ, measures of IQ. We can say it's not valid. It's not a way to measure intelligence. SAT is not a way to measure aptitude or ability level in college. I don't even think they even know what SAT measures. I don't think it really measures anything, personally. What does it measure? You could solve a couple problems and you can memorize a few words. Does that mean you're going to be successful in college? Probably not. And when they looked at they tried to predict college GPA based on SAT, and they did the regression on it, they found a very weak relationship. So it's not really giving you that much. So standardizing a distribution has two steps, as I mentioned on the last slide. You transform the raw scores into z-scores, and then you transform those z-scores into new values, new x values based on the mean and the standard deviation, like you have with IQ. So you transfer over the z-score, and then you transfer onto this new scale. So it's two steps, but it's just the same linear transformation that you're doing with a z-score. You're doing it back to a raw score. So let's say that we had the original score. The original mean is 57, and the standard deviation is 14. So that was the original scores. Mean of 57, standard deviation of 14. Well, now we convert them to z-scores, so the mean obviously becomes 0. The standard deviation is always 1. And now we convert those z-scores to an alternative new score. So we're not converting them back to the original metric. We're converting it to a new metric with a mean of 50 and a standard deviation of 10, and we're just mapping those z-scores onto those to this new metric. Does that change the meaning of the scores? No. The scores mean the same. The relationship between scores and the distribution stays the same. The only thing that changed was the mean and the standard deviation, which means from a statistical point of view, doesn't mean very much, right? It's like applying a curve. Let's say your original score on the test was 40, and I said I'm going to give you a 30-point curve. I've just transformed your scores to a new distribution that's 30 points higher, i.e. the curve. So now, let's say the mean was 40 before, and I added 30 points to all the scores. Now the mean is 70. The relationship between the scores is the same. I add 30 points to every score, but the mean changes. So now it looks like a completely different measure. Before the mean was 40, now it's 70. Seems a lot better, right? Same scores, I just transformed it to a new distribution. Let's look at a couple more of these learning checks. Score of 59 comes from a distribution with a mean of 63 and a standard deviation of 8. The distribution is standardized to a new distribution with a mean of 50 and a standard deviation of 10. What is the new value of the original score? So we're transforming the original score of 59 to a completely different distribution. So the first step is find the z-score. So the z-score based off the original score of 59 is going to be 59 minus 63 divided by 8. 59 minus 63 is negative 4, divided by 8 is negative 1/2. Now take that z-score of negative 1/2 and put it into the new distribution. If the mean is 50 and the standard deviation is 10, and the person has a z-score of negative 1/2, it's going to be half of sigma subtracted from 50. So it's going to be 50 minus 1/2 of 10, which is going to be 50 minus 5, which is going to give a new score of 45, which is B. And this is exactly what we did. So the first step was find the z-score based off the original score and the original distribution. Once you calculate that z-score, plug it into the new distribution with a mean of 50 and a sigma of 10, and solve for the new score, the new raw score. And that's all we did, is we changed over from one distribution to another. We're going to be using z-scores a lot more when we get to looking at inferential statistics and outliers, and how extreme does our results have to be to indicate that something's going on. Either someone is screwed up, or something's wrong with the test or the measure, or there's a difference in our treatment compared to the original population. Our treatment made a difference because our scores became extreme after the treatment. And we can find this using z-scores. So for example, if I gave you some kind of treatment for a deadly disease, and now all of a sudden the amount of time you lived greatly increased, if I compare that value that greatly increased based on the new treatment compared to what people originally had given no treatment, I would expect that value to be very extreme when compared to the population that did not get any treatment in terms of life expectancy. And that extreme score would indicate, that extreme z-score would indicate that that score does not belong with the population of people that got no treatment. Therefore, the person that got the treatment worked, because that score is very unlikely to belong to the population of people that did not get treated at all. So therefore it belongs to some alternative population where the treatment works. And although that sounds kind of confusing, because you're not really familiar with hypothesis testing, um, think of it this way, that if the z-score is extreme, is very high or very low, compared to the status quo, or what is called the null hypothesis, then we can say that the null hypothesis or the status quo is fundamentally different, and that the intervention or the treatment actually works. And although we just don't use a single z-score to make this decision, we could use a sample of people and compare it to a population parameter if we know that population parameter, and we can compute a z-score that way. And that's done very often if we know the population mean and the population standard deviation. If we don't, then the z-score is not going to help. So the z-score only helps if we know the means and the standard deviations. If we don't, then the z-score needs to be replaced, and the population means and standard deviations need to be estimated. And things get a little bit trickier then. Then we need to move away from z and move on to t, or some alternative distribution, which we will get to in time. You're going to be seeing z, you're going to be seeing t, you're going to be seeing ANOVA, you're going to be seeing correlation, you're going to be seeing chi-square. So we have all these inferential tests to come. We're going to be getting to this. There's a lot, and this is only the very basic stuff. I kept the scores very, very basic. It gets so much more complicated, but these are the foundational tools that you're getting. And then when you go to graduate school and you move on and you want to take more of the stuff, you can take tons more of the stuff. You could break out calculus, you could break out the linear algebra, you do all that stuff if you want. So in our study, we have an original population that does not get treatment. So let's say this is for a deadly virus. Where did I hear about a deadly virus? Okay. And let's say that I want to see if the new treatment doesn't work to treat this deadly virus. I take a sample of individuals and I give them this new treatment. I then compare this treatment, these people that got the new treatment, to the original population that got no treatment. I'm hoping that the new treatment is going to be superior to the no treatment group. One way I can determine this is by calculating a z-score. So whatever your z-score is after getting treated, I would expect it to be very high or very low compared to the no treatment group because I expect there to be a difference, right? The treatment's going to work, then after treatment, your score should not be the same as people that got no treatment. So therefore, your z-score should be extreme, either positive or negative extreme. And that's kind of the conceptual basis of this. There's a lot more to this, but that's kind of the take-home point is, after you get treated, do you belong with the original population that didn't get treated, or do you not belong with that population anymore? And the goal of any researcher is to have to have the people getting treated to not belong with the population that gets no treatment. Because if you belong in the population that gets no treatment, then the treatment obviously didn't do anything for you. You want to have some kind of difference. And so the text talks about, extreme scores that have a score above 2.0 or negative 2.0. That's helpful as far as hypothesis testing, that if you're getting treated, you don't want to be close to the mean of the non-treated people or animals, in this case, rats, right? So this is the weight of rats. So if you're getting some kind of treatment, you want to not be with the rest of the non-treatment group. So the non-treatment group has a mean of 400. You want to be far away from 400 if you're getting the treatment, right? So any rodent here that gets the treatment should be far away from 400. Now, how far do you have to be? Depends on the standard deviation. Here, the standard deviation is 20. So if I'm 2 standard deviations above the mean, the rat's weight would be 440. That's pretty far away from 400. It's 2 standard deviations above the mean. If you're 2 standard deviations below the mean, the rat's weight is 360. That's pretty far from 400 as well. So you want to be kind of in the tails of this distribution when you're getting the treatment, because that means the treatment is having an effect. If you get the treatment and you end up close to 400 here in the middle of this distribution, then the treatment is not doing anything. And therefore you're kind of screwed. As a researcher, you're having bad results and back to the drawing board and coming up with a new idea. So as a researcher, you want to be far away from the non-treated people, rodents, animals, etc. You want to be in the tails of the distribution of non-treated individuals. That's the goal. Now, the further in the tail you are, the better. Do you want to consider 2 good enough to reject the null hypothesis? Is that extreme enough? Depends on the level of certainty you want. So it depends on something called type 1 error. So are you willing to make a mistake or not? If you're okay with making a mistake, then a z-score of 2 would probably be okay to say that your treatment worked. If you want to minimize the chance of making a mistake, then you want to make the z-score much higher to be able to say that the treatment had an effect. So it really depends on what probability of making an error that you want to allow yourself. And so we're going to get into this idea of null hypothesis, research hypothesis, type 1 error, type 2 error, because hypothesis testing is not yes or no. It's always based on probability. It's always likely versus not likely. And even if something is likely, there's always a chance you're making a mistake. There's never 100%. You're never going to be 100% sure of anything with statistics. You're not going to have a probability of 1, and you're not going to have a probability of 0 in research. You're going to have things in between, and you have to decide how much error am I willing to live with as a researcher. And we'll talk all about that when we get to hypothesis testing. But this graph kind of shows you that you want to be far away from everybody else. So if you're getting the treatment, you should be in the tails of the distribution of individuals or animals, etc., that get no treatment. They're the control group. You want to be away from the control group. And in this case, if you're in the tails, you're more likely that the treatment actually works. Let's look at another one of these, a couple of these slides. Last week, Andy had exams in chemistry and in Spanish. On the chemistry exam, the mean was 30 with a standard deviation of 5. and Andy had a score of 45. On the Spanish exam, the mean was 60 and a standard deviation of 6, and Andy had a score of 65. For which class should Andy expect a better grade? Well, once again, we want to compare these z-scores because they're in different classes. I can't just say that Andy scored better on Spanish, and therefore, Andy did better in the Spanish class compared to the chemistry class. That's not the case. Yes, Andy scored higher on the Spanish exam, right? Andy scored a 65 on the Spanish exam, scored higher than on the chemistry exam. But you must compare Andy's score relative to the rest of the class. And that's what the computing the z-score means. So in the case of the chemistry class, the mean was 30 and the standard deviation was 5. Andy scored 45. So if I plug that into the formula, z is x minus mu over sigma. So z here is 45 minus 30 over 5. So that gives me 15 over 5. That gives me a z-score of 3. That's outstanding. So Andy scored great in the chemistry class because everybody failed miserably, and Andy did better than these people. Andy scored a z-score of 3, which is really, really high. There's probably nobody higher than Andy in this class, if it's normally distributed. On the Spanish exam, Andy scored 65, but the mean was 60, and the standard deviation was 6. So if I plug it into the z-score formula, 65 minus 60 divided by 6 gives me 5 over 6, which gives me about 0.80, 0.81, around that, less than 1. So the z-score is less than 1. So Andy scored very close to the average, slightly above average in the Spanish class. But in the chemistry class, Andy scored tremendously high. So Andy did better in chemistry than Spanish, even though the raw score on the Spanish exam was much higher. Andy did better relative to everybody else in the chemistry class. So the answer is chemistry. And this is just simply comparing the z-scores and then determining that the z-score for chemistry was 3 and the z-score for Spanish was less than 1. So chemistry by a lot. Andy performed better in chemistry. Let's look at these true-false questions. Transforming an entire distribution of scores into z-scores will not change the shape of the distribution. And the answer is true. Once I'm transforming from the original distribution to a z-score distribution, the shape of the distribution always stays the same. And in the second true-false statement, if a sample of 10 scores is transformed into z-scores, there will be 5 positive z-scores and 5 negative z-scores. Well, that would be only correct if the distribution of 10 scores was symmetrical. That means the left side and the right side were mirror images of each other. So if it was symmetrical, then that would be the case. There'd be 5 positive and 5 negative z-scores. But if the distribution was skewed, which is not symmetrical, right? There's a tail, then this is not the case. Because remember that if you're transforming to z-scores, you're keeping the shape of the original distribution. So if the original distribution is skewed, then the z-score distribution will also be skewed. And you're not guaranteed to have 5 and 5. That's a symmetrical distribution. So that answer would be false for that one. That's exactly what we have here. So hopefully this is sort of an overview of this that you may be familiar with this already, I'm not sure. But please practice plugging in the numbers, doing the homework, etc., doing the equations, because you're going to have some very basic stuff for the homeworks and then obviously for the exam coming up. So there's so much more to this. This is the very, very beginning stuff, and this is very, very basic. Generally, there's a lot more detail involved, but since the class is online, I'm kind of going really slow and doing some basic stuff at the beginning. So take your time to understand the foundational material, study it, be able to do some basic problems, go online on the Mind Tap and do the practice problems, do them again and again and again, and do them on paper. You don't have to do it all in your head. You can do it on paper too. make sure you can figure it out. So when the exam comes, you're going to have a mixture of multiple choice and some very basic computations. Nothing mind-shattering, nothing very difficult. Because it has to be, the exam has to be online. So there's a limit to what I can ask. But hopefully that's a pretty decent overview for Z-scores. Go read the chapter, start working on the homeworks, start doing the lab and all when you get a chance. And if you have any questions, let me know. And I'll see you next time. Bye for now.